Yes, hi and welcome everyone to this 1W-MINDS seminar. Today's speaker is Anders Hansen. He is a professor of mathematics at the University of Cambridge, where he leads the Applied Functional and Harmonic Analysis group, and also obtained his PhD in 2018. He has won numerous prizes and is a fellow of the Royal Society. His research resides in the borderline of applied mathematics and theoretical computer science, and often question our understanding about what mathematics really can or can't do. Today he's going to speak about Smale's ninth problem, generalized hardness of approximation and the limits of AI. The floor is yours, Anders.
Great, thanks a lot. Thanks a lot for the generous introduction. Let me just mention that this is joint work with Viktor Antun, Alex Bastunis, Mac Holbrook, Lutza Gastek, and Werner Vlacic. And before I start off, I'm going to start with a collection of numerical examples. And I'm going to start very basic with a rather innocent linear program. So here it is. And I have this delta parameter here that I'm going to vary. And what I'm going to do is that I'm going to simply test the standard software that we have that I like typically, which is MATLAB's linprog command. Linprog, as in linear program, is the standard MATLAB routine for solving linear programs. Linprog has a very nice feature, namely this exit flag. So there's tons of things that could go wrong, but there's also things that could go right, and experts will understand exactly what this means. Right now, I'm interested in, do I get a 1 when it is happy and the solution is certified as correct, or do I not get a 1? But of course, this exit flag is extremely important because this is a part of making trustworthy algorithms that we all want. Fine, let's see how we do. Now, linprog has 3 different choices of algorithms. These are the names that they're called in MATLAB: dual simplex, interior point, and interior point legacy. What you see on the left-hand side here is the value of the delta parameter that are presented in the linear program. And we know the error, and the error is listed here. This is the L2 error of the minimizer. And as you can see, we do very well in the beginning, universally. Exit flag, everybody's happy, perfect solution. And then suddenly we are getting complete garbage. And the exit flag certifies the garbage as correct, universally. Slightly different behavior here, but the message is the same. The question is, of course, why? Now, here's another example. A not so innocent problem, but still slightly innocent, reasonably innocent. This is a lasso problem. Everybody knows the lasso problem. We're doing the same thing. We want to test MATLAB on this. This is the lasso command we're going to test, and we're giving the machine this example here. Again, with delta that I'm going to change. And mind you that this is now a centered and standardized problem. This is exactly what statisticians would normally expect in a lasso setup. We're going to test how the computational tools will work on this. Now, MATLAB's lasso does not have this really nice feature of an exit flag, but it does have a warning. And this warning comes up when it sniffs that something is wrong. So what I've indicated here is a 0 if there is no warning, and a 1 if the algorithm produced a warning. Here is the value of these deltas. And as you can see, the behavior is very reminiscent of what happened with linear programs. We do well in the beginning, and then very quickly we start getting garbage, and there is no warning. Now, the lasso command will have the opportunity to, for example, change the relative tolerance in the code. Suppose we set that to the machine precision, slightly different behavior. In the beginning, we do well. Now, there's at least a warning. Something is wrong. It sniffs that something is wrong. But eventually, for small enough deltas, we get garbage quickly and no warning. Now, to squeeze this code to the ultimate, we set the maximum number of iterations to be the inverse of machine epsilon. In that case, we get good stuff in the beginning, and then here we simply give up after 12 hours. Mind you, no warning. And eventually we get garbage quickly and no warning. The question is, why? And of course, that's what we're interested in. And if we can see if we can mathematically explain this. Now, let me start with linear programming. And linear programming, as you have seen in many of its forms, here it is in one of its basic forms. I'm not going to talk a whole lot about that setup because you know it very well. What I want to point out is that it's the minimizer we're interested in, not the whole argument, but one element in the minimizer, or in the set of minimizers. And the reason why is that in mathematics of information and data science, it's typically the minimizers that are of interest, not interested in computing an approximation to the objective. It's the minimizers. Now, linear programming is probably one of the most investigated problems in computational mathematics. But despite the fact that there's enormous literature on this, there are big problems left. So serious that the Smale's ninth problem highlights this and asks simply, is there a polynomial time algorithm over the real numbers which decides the feasibility of a linear system of inequalities, ax greater than or equal to y? And if so, outputs an x. In other words, can you detect feasibility of a linear program and compute at least one minimizer in polynomial time? Now, this problem here is phrased in the BSS model, the Bloom-Shube-Smale model, where we talk about computers that work with real numbers. If you're a computer scientist, this problem here would typically be phrased as, is there a strongly polynomial time algorithm for linear programs? I'm going to talk a little bit about that subtlety in a couple of slides. Anyway, so this is Smale's ninth problem from the list of problems for the mathematical problems for the 21st century. But Smale also mentions, and this is really important typically in applications, but real number computations and algorithms which work only in exact arithmetic can offer only limited understanding. Models which process approximate inputs and which permit round-of computations are called for. And if you're working in applications, this is something for which you will embrace immediately and say, yes, of course, this is happening on a daily basis. Simply because, well, I use root on a daily basis. I use cosine, I use exponential, simply because I may use the discrete Fourier transform. I compute the 2 norm a lot. That means that I'm going to do a root. So all of these numbers that are irrational can, of course, not be stored with a finite amount of information on a computer. So you'll end up having to approximate them. But there is a very important thing that I want to highlight, because this phenomenon happens even with rational numbers. So if you're running floating point arithmetic, then you're going to be working in base 2. Typically, then what happens is that an innocent number like 1/3 is not stored as 1/3 on the computer. It's stored as a base 2 approximation term. So the problem of approximations happen regardless, unless you are actually in base 2 and have specific, of course, in the floating point setup that there will not be all numbers in base 2 that you will store. Okay, so what is known about linear programs? Well, linear programs are in P. They're polynomially solvable, right? I mean, it must be true. It's on the front page of the New York Times. Not a lot of mathematical problems reach the front page of the New York Times. So this is the legendary ellipsoid algorithm announcement, the work by Kachan. You can see it here. And the issue is the following. It's true that LP is in P. And what that means, and I'm not using the ellipsoid algorithm here, I'm using Karmarkar's algorithm because of the better complexity bounds. What this means is that you can solve a linear program as follows, with the following complexity bounds. N here is the number of variables in your linear program, and L here is the number of bits, or the number of digits, if you will. And so this here is typically the bit complexity, but the number of arithmetic operations also behave like this. And that's the bizarre thing, because if I plug in, say, pi here now, can I solve a linear program with pi? Well, pi is going to have, L is going to be infinite. So here is the problem then with Smale's ninth problem. We don't know if you can actually remove this. And here's the issue. I'm not really interested in L. I'm interested in K, where K should be the number of correct digits in my output. So suppose I will like say 5 digits on my minimizer. How big should L be? Should it be 5, 10, 10 to the 80? What should it be? The point here is that the standard theory won't cover this. So the basic problem is really this. Given a class of linear programs that contain irrational numbers, which can be computed in polynomial time, what's the computational cost of computing a k-digit accurate approximate minimizer? Is that problem in P? And as I mentioned here, the previous estimates are not going to help us very much because, well, plugging in L equals infinity is not going to give us anything. All right, so this is now the setup for this extended Smale's ninth problem, which I'm going to talk about. And the way you can think about this extended model, which, by the way, is not something that Smale cooked up, this idea of having an approximation is, of course, something that you'll see throughout mathematics. From a practical point of view, you can think about this as you can use MATLAB, for example, or some other software that has a variable precision command. So you can think about this variable precision command as something that you can call as often as you want. Do I need 5 digits, 10, 50, 100, and so on and so forth. So it's an oracle that you can consult. So I can ask for however many digits of pi that I want. Now, this extended model here is much more complicated when you do the analysis than the standard typical way that we do. And so this, I want to highlight, has been used in many cases. If you're really interested in some of the technical issues here, there's a series of papers by Pfefferman and Klartag in the Annals of Maths from the mid-2000s, where they do computations of function approximations via optimization. In one of those papers, they do the full extended model, and that paper becomes about 150 pages long, so it becomes technical. Okay, I have talked about linear programs, and the issue here is that it's not only linear programs that's the core of modern mathematics of information and optimization problems there. You have semi-definite program, basis pursuit, lasso, the unconstrained, the constrained versions of this. And all of these problems here have been completely essential in the development of modern mathematics of data science and information. And to highlight this, I want to highlight some of the most cited papers in mathematics of information over the last decades. These 4 papers here have about 100,000 citations altogether. And what they have in common is that they rely on algorithms for computing minimizers of at least one of these problems on this list. Okay. So now we can get to the extended Smale's ninth problem. And to be able to state this and formulate a theorem, I need to introduce a little bit of notation. Now, the psi here is going to be the solution map. Think about a linear program taking in the constraints, and then it spits out the set of minimizers. Okay. The double arrow here means that this function here is multi-valued. The set of minimizer does not have to be unique, but this is really crucial. Note that in Smale's ninth problem, one asks about one minimizer, not the whole set. So I will never demand that the algorithm should be able to compute more than one. So when we measure the error, the algorithm is going to be single valued, and we're only interested in the distance from that single valued output of the algorithm to the set of minimizers. That's really important. All right. So the extended Smale's ninth problem is simply saying, okay, let's take the original Smale's ninth problem and add more complexity to it by saying what happens even when you have the extended model where the input is also inexact but can be given to arbitrary precision, which is what you would actually do in real life computation. So it really simply says, given any of these problems on that slide 17, doesn't have to just be linear programs, semi-definite program, lasso, and so forth. Suppose now that we have a solution map of that. And the question now is, if there is an algorithm that can decide the feasibility of the problem, and if so, produce an output that's correct up to k digits, and whose computational cost is bounded by a polynomial k and the number of variables n. And this problem here has a very delicate theorem accompanying it. This theorem looks a bit horrendous. And the reason why it is horrendous is that all of these things here, which I'm going to comment on in detail, happen at the same time. So what I'm going to do now is I'm going to try to read it out and explain all the subtleties. And then later on, I'm going to talk about how this relates to other areas of mathematics, and particularly AI. So let's start. Let psi be any of these solution maps. Think linear programming, because that's what we all know very well. Choose your favorite p-norm. This is how we're going to measure the error. And choose an integer k greater than 2. The reason why that has to be greater than 2 will be evident in a couple of minutes. Now, there exists a class omega, so omega now depends on k. Given a k, there is an omega. That means a class of linear programs. So that all of these things here happen simultaneously for that omega, right? The first statement is, no algorithm can produce k correct digits on the inputs in omega. And you can't do better than coin flipping in the case of a randomized algorithm. Now, number 2 here is a bit of a paradox, and we're going to comment on that in detail later on. If we allow the randomized algorithm to have a potential non-zero probability of not halting, then you can boost the probability to 2/3, but not beyond 2/3. And if you're a computer scientist now, you probably think that I'm completely bonkers, because the wisdom is that you cannot get better than a half for problems that are non-computable. And if you were able to get better than a half, you should be able to rerun the algorithm several times and get a probability that's arbitrarily close to 1. So this sounds completely bizarre. I'm going to comment on that a little later on. But remember, you can't do k correct digits. But if you're a little less greedy, on the same class omega, you can compute k minus 1 correct digits, but that's going to take you arbitrarily long time, meaning any algorithm can do that, will have, for any time, say 50 billion years, an input so that it's going to run for longer than 50 billion years and still not achieve the k minus 1 correct digits. But he might get it after, say, 50 billion and 1 years. And you can also characterize this in terms of probability. Now, finally, if you are a little less greedy than that, you can get k minus 2 correct digits in polynomial time. And now you see this k greater than 2 was simply there to be able to have this k minus 1, and k minus 2 effect. And what you see here are these phase transitions. So what it says is that choose any k, it can be 5, it can be 59, it can be whatever. Then there exists a class of linear programs for which you're going to have phase transitions between the accuracy that you can compute. Moreover, there's a bizarre phenomenon of how actually randomness can help this in a non-intuitive way. And this is the phenomenon of generalized hardness of approximation, which I'm going to try to put in perspective in a second. But now I want to comment on this bizarre thing about that probability, because the classical wisdom, due to a legendary result, is that randomness does not help non-computability. And some of you may know this very well. This is a legendary volume in the Annals of Maths Studies from 1956. And as you can see here, The authors here contain some of the finest minds at the time, focusing on foundations of computation. Modulo Turing, this was printed in 1956, and Turing had passed away before that. Anyway, so now you're thinking, you know what? I probably believe these guys more than me, the speaker. And I would be inclined to agree with you there. But there isn't any discrepancy between this legendary result and what we're saying. And it's a very, very subtle issue. The result here holds for single-valued functions or single-valued problems. What we're talking about here are multi-valued. And that makes these problems here strictly easier in many cases. And that's why it works. In fact, this 2/3 can be arbitrarily chosen. But when it's chosen to be some number close to 1, you cannot go beyond it. You can't rerun the algorithm. So 2/3 here is one specific example, but I could change the omega so that you can get another number there as well. But it does not contradict this seminal result from 1956, simply because these are completely different problems. And the wisdom has to be slightly adjusted here. Randomness does help non-computability, particularly in optimization. For this very, very subtle reason, we're doing multi-value problems. Okay? So there's another sort of initial thought that people in computation will have. And that is that there's something fishy going on here, potentially with condition. So the wisdom is that, ill-conditioned things can be bad, well-conditioned things can be good, right? We're not cheating here. All of these condition numbers here are bounded in the theorem. And of course, the condition number of a matrix doesn't make a whole lot of sense in a linear program, because a linear program, you can have a matrix that is not invertible. So this refers to, say, AA star in this case. So there's nothing here that makes this ill condition. I just see that there's one in the chat. Why don't I actually, let me just, hi, Felix. I don't know the result by Shannon, but I guess they assume that the randomized algorithm always halt. Oh, that's a great question. Yes. No, they don't. This is super important. Very good question. Let me address that. No. So it's not this issue that you get the boost with the non-halting. This here is exactly the same thing. You see, all of this here is for a randomized Turing machine. A randomized Turing machine doesn't have to halt. So it's a very good point. No. You cannot boost these problems here beyond a half, even if you allow your algorithm not to halt. It's a very good point. Did that make sense? Yeah, excellent. But this is really subtle. I'm very glad you pointed that out, Felix. Great. Because the point here is this: it is not that is not the fact. There's a lot of other mechanisms here, but this theorem here also covers the potentially non-halting algorithms. Great. Okay, so now I want to talk about generalized hardness of approximation. And I want to talk about this now in the context of hardness of approximation first, okay? So hardness of approximation, and you may know about these things, is an area within computer science, completely sort of discrete mathematics. And typically what you end up in hardness of approximation is that you have a combinatorial problem that you would like to solve, say traveling salesman or something like that. And then you realize that this is going to be an NP-hard problem. And what one tries to do then to compensate for that is to be a little less greedy and say, what if we can compute now the optimum with some error, an approximation to it? So some epsilon approximation to that optimum. And then what happens is that typically you'll have this phase transition. There's an approximation threshold. So when that epsilon is greater than this threshold, the problem might be easy. It might be in P. And then suddenly, if that epsilon now is smaller than this threshold, it changes completely, and now it becomes NP-hard. And then it's NP-hard all the way, of course, for epsilon equals 0. And that's the word hardness of approximation, right? So hardness of approximation is a very well-established area in computer science. What I'm talking about here, this phenomenon here, is a generalized version of that, but for completely different mathematical reasons. So there's no sort of discrete P versus NP here, which is really crucial for hardness of approximation. Hardness of approximation in computer science, you may not have these phase transitions if, for example, P is equal to NP. Not that I believe that that's the case. So if P is not equal to NP, then you will have these phase transitions. But what I've talked to you about today in optimization has absolutely nothing to do with that. Okay, so what happens now in optimization, and it will happen in a lot of other areas, in inverse problems and in AI, as I'm going to talk about a little later on, you will have exactly this behavior where computing the problem can be in one class for epsilon greater than some threshold. It might be easy, say in polynomial, in P, it's polynomially solvable. And then suddenly it jumps and it becomes not polynomially solvable if that epsilon is less than this threshold. And what I mentioned to you today are much more generalized version of this, for which you can go from being polynomial to suddenly jump and be not even computable. And this k minus 1, k minus 2 phenomenon shows that there is more than one phase transitions. You can have many of them. For all that I know, you can have infinitely many different types of problems. So this is just a beginning to essentially try to classify and understand this phenomenon and figure out in which areas will they occur. I want to point out that the classical hardness of approximation has been a huge field in computer science. You can recognize some of the leading field here, leading people in the field. The first Gödel Prize was in 2001. I think there's in total 5 Gödel Prizes now for hardness of approximation, and Neville Prizes and ACM awards as well. Just want to mention that for completeness of the history. Okay, but now I want to essentially get to another question, which you should ask yourself, and that is, why do I care? And the why do I care question is really important. And what I mean by that is that grumpy mathematicians like myself have a tendency of cooking up examples that are true, but they might be rare. And the practitioner is going to say, well, you know what? I really don't care about these really negative and pessimistic results if I never see them. So what I'm going to do now is I'm going to show you a random case. And I'm going to do this with basis pursuit and unconstrained lasso. In fact, I'm going to do this with basis pursuit with that delta equals 0. And that means it is actually a special case of linear programs. And I'm going to feed in a random matrix, IID, with some different distributions. And I'm now going to try standard algorithms on them and see what happens. So these two graphs here are this is for the basis pursuit. So it's actually a linear program. And I'm using SPGL1. I want to say we're using SPGL1 here, not because it's bad, because it's really, really good. And no other algorithm would be able to do better on this. It's the same issue. You won't be able to beat this. It's not that SPGL1 is bad. What we've done here is to show the success rate. We try and compute minimizers of these problems, where the input now is an 1 by n matrix, which is IID, with different distributions. The success rate is the number of successes divided by the number of trials. There's 1,500 trials in each example. And then you see the score here. So that's a number. The success rate is the number between 0 and 1. And what you see here are the different asymptotic behaviors for different ensembles. So this is uniform in the interval 1 to 10. This n here stands for the normal distribution. Here's the variance. Sorry, here's the mean. This is the variance. And here the exponential is exponential distribution, in this case with lambda equals 1. And here's the important part. The definition of success is k equals 2 digits. So 2 digits or better, then we're happy. And you can see now that the probability of success tends to 0, particularly for a uniform distribution. You see a very different behavior. For the normal distribution, this also tends to 0, but it's going to be very, very, very slow. We don't know what happens to the exponential here. That's very, very close to 1. But what you see is the similar behavior. And as n grows, the probability of failure actually increases. So the point here is that this is not a rare phenomenon. And what you actually see here is this phase transition type of phenomenon, generalized hardness of approximation in practice. So in this case here, k equals 2, and you will have an omega now with problems for which you have a phase transition at k equals 2. And what roughly happens here is that there's a probability, I have an ensemble, there's a probability that you end up essentially in this class here. And this is what you see. So in this case here, the probability of that actually grows. Now, of course, this is completely numerical, but that's also the purpose. You will see this phenomenon in front of your eyes on a daily basis on your computer. This is not sort of pure math, mumbo jumbo. Okay, now, you may say that these problems here must be within what's called robust optimization. And I want to highlight that robust optimization is a fantastic field, incredibly interesting, pioneered by people like Arkady Nemirovsky and co-authors El Gahoui and Ben Tal. And there is no discrepancy between these results that we have and classical robust optimization. Classical robust optimization is about computing approximations to the objective, not the minimizers. And what these results show is that if you actually want to do robust optimization on the minimizers, you will see this generalized hardness of approximation phenomenon. All right. Now I am going to turn the question upside down. So the first theorem I showed you, then we saw that you will have these phase transitions. Any kind of K is going to give you phase transitions. But now I want to turn the question around and say, what if we take a class of problems in the sciences and ask, is there a phase transition? And if so, what is it? And this is typically what computer scientists do in hardness of approximation. They will say, oh, here we have a class of problems. What is the phase transition? And if you get that sharp, then that's when you open a bottle of champagne and potentially get a paper in the top journals like JAMS or Annals or something like that. So now we're going to take a very standard problem in the sciences, namely basis pursuit, which is, of course, the basis for a lot of sparse recovery compressed sensing type of problems, and also this robust null space property. If you never heard about the robust null space property, then it doesn't matter. But this is sort of a key property that ironically actually happens with high probability in the science for many ensembles, and this is sort of the core part of sparse recovery. So it makes sense to ask, what happens for these problems here? Will there be a phase transition? And if so, where? So, simple question, given basis pursuit, now I'm asking, what is the approximation threshold for the class when I have robust space? Now there's, yeah, very good. Okay, so now I need to be slightly more formal because I'm going to present a theorem. So what we're going to do now is that we are going to, for fixed dimensions, now take all the problems for which satisfies 10. So this is, we have the robust null space property. Here is my epsilon. These are parameters, and I have my rho, and I have my tau, which are the parameters in the robust null space property. And then I take all kinds of problems like this and simply make the union of this. And that's the class we're now going to consider. So it's essentially all problems with the robust null space property. Before I show you the theorem, I want to highlight one really, really important thing, and that is this Renegard condition number. This Renegard condition number is crucial because I want to show you a very subtle phenomenon in a second. This Renegard condition number is 1 over the distance from your problem to another problem that has several minimizers. So it's ill-conditioned if the problem has several minimizers. So it will be infinite if you're on the boundary of problems that have several minimizers, or it has several minimizers. So having unique minimizers is good according to this condition number here. And now I want to show you the theorem which is long and a bit cumbersome. So I'm going to be quite quick about this because I don't want to run out of time. But here's the crux. There is a phase transition, and it can be characterized. It's here. Now you see, this is the bounds, upper and lower, and we're almost there. It's a constant off here for this phase transition. It could be that there's tons of other phase transitions in between. We wouldn't know, but it's a constant away. But here's the interesting part. You see, what's this delta here? That delta is this guy here. That's the noise parameter in basis pursuit. So this is, in some sense, a bittersweet, but much more sweet than bitter result. There is a phase transition, but the phase transition scales with that noise parameter. And if that noise parameter is 0, there's no phase transition. So this also tells you why things work. In fact, when you have these conditions, you have polynomial algorithms to solve them. And you're not going to do worse than the noise. And if there's no noise, everything is fine. But here's the slight paradox. You see here, that is infinite. This condition number, the Rengar condition number here, is infinite for problems in that nice class when there isn't any phase transition. And so the point that I want to highlight now is that this generalized hardness of approximation cannot be characterized through condition numbers. I showed you these other condition numbers for which can be finite, and you can have phase transitions. And you can also have the case where there's no phase transition and everybody's happy, but there will be infinite condition. So this is a very subtle thing. That does not mean that condition numbers are not great, they're fantastic. But this phenomenon here is extremely subtle and has essentially facets that go way beyond just the standard understanding that we have of condition. Right. I am a little worried that I might be running out of time, so I need to speed things up a bit. So I'm going to be a little brief on this part here, but this also is important, so I want to highlight it. What we have covered so far can explain this part here. It can explain why dual simplex fail, interior point legacy, all of these guys are going to fail. That's fine. But the theorem that I showed you does not tell you why the exit flag fails here. And that's an interesting and also a subtle problem. I want to show you a result on that. But before that, I want to mention it is very simple to make the exit flag problem completely trivial. And we want to avoid that. So think about now, if you create a code, an algorithm for solving linear programs that always spits out Mickey Mouse, then I can create an exit flag for that algorithm, which says if Mickey Mouse, exit flag is 0. And I will be correct all the time. That's not particularly interesting. So what you need to make sure is that you make it non-trivial. And that means that the algorithm must spit out something which is in the range of your problem function. It doesn't have to be close to the solution, but it has to be close to the range. In other words, if you're going to compute linear programs, Mickey Mouse is not allowed, right? When you have that assumption, then it becomes interesting and non-trivial. And in the good tradition of showing you lengthy and horrendous theorems in this talk, here is another one. I'm going to be brief. You can read about this if you're interested in the paper. What it says is that you cannot compute the exit flag, which kind of was what you were expecting, given the buildup. But there's another sophistication here that I think is important to highlight, and that is that the exit flag is strictly harder than the original problem in many cases. So what MATLAB tries to do is not only impossible, it's actually harder than trying to compute the original linear program. And that's a subtlety which I think it's important to get through. Right. Okay, fine. I think I can, if I'm going to wrap up in about 8-9 minutes, I think I can pull this off. All right. So now I want to talk a little bit about this generalized hardness of approximation and understanding the non-computable in the context of other areas, particularly artificial intelligence. And I want to mention briefly that this is a part of a greater program on the solvability complexity index hierarchy, and a lot of these tools are essentially developed within that system. And to talk about the limits of AI, I would like to highlight this story here that was published in IEEE Spectrum in 2021. They summarized everything they had on AI for that year. And I want to read from the intro. 2021 was the year in which the wonders of artificial intelligence stopped being a story, which is not to say that IEEE Spectrum didn't cover AI. We covered the heck out of it. But we all know that deep learning can do wondrous things and that it's being rapidly incorporated into many industries. That's yesterday's news. Many of this year's top articles grapple with the limits of deep learning, today's dominant strand of AI, and spotlighted research seeking new paths. Indeed. So now what you see is that there's a really growing interest in understanding the limits of AI. And of course, when talking about limits of AI, this goes directly into the issue of foundations of AI. And we're, of course, not the only ones who are interested in this, but I do want to give credit to people who I view as pioneers when it comes to asking questions and pointing things out. In particular, Ari Rahimi mentioned in 2017 the now quite famous quote, how he likens machine learning and modern AI to alchemy. Now, that didn't go down well with everybody, and if you haven't seen this discussion, I highly encourage you to Google it. It's a fascinating debate. Regardless if you agree with Rahimi or not, what I think is important is that we can all learn from the alchemists in the following way. What would the alchemists want to do? Well, they wanted to create gold. How did they do it? Well, they were not able to create gold, but how did they try? Well, they would buy a pot, add a little bit of green, a little bit of yellow, stir, and see, is there gold? If it doesn't work, add a little bit of red to it, a little bit of black, a little bit of yellow again, and stir, and you can continue this iteration forever, and you will never reach gold. And the crux here is the limits. The point is that research methodology will never be able to understand why you cannot create gold. You need a completely different research methodology to understand the foundations, and in particular, the limits. And what we see now with the lack of understanding of limits and the foundations of AI, we are quite close, in fact, very, very similar situation to the situation in mathematics in the beginning of the 20th century, where the word crisis was really used about its foundations. And you had, of course, this led by David Hilbert, and then these other legendary researchers in the field, Turing, Gödel, and Russell, that participated in this program of getting the foundations and typically, very importantly, the limits of mathematics and computation. And as we all know, Turing and Gödel turned this field completely upside down. So we're in a very similar situation now with AI, for which the foundation, the book of foundations and understanding of limits is still very, very thin. And it's thin, even though it is one of the problems on Smale's list of problems for the mathematical problems for the 21st century, where essentially he makes the argument about the importance of understanding the limits of AI, of course, building on the great tradition of understanding the limits in mathematics and computations. So now I want to put this in perspective to the results that I've talked about today. So I could talk about these things for hours, and I just want to point you to this paper here if you're interested, because the generalized hardness of approximation phenomenon will happen also when you want to compute neural networks. And a delicate issue here is that you can end up with a situation for which you can prove that there exists a both accurate and stable neural network for your basic problem, but you won't be able to compute it depending on the accuracy. There will be a threshold, this approximation threshold, also in the cases where you want to compute neural networks. And that's really a delicate issue, because what that means is that you can prove existence of neural networks as much as you want. The question is, which one of them can you actually compute? And the point is that it might not be of interest to compute this to arbitrary precision. No. What you need to understand is simply the threshold. If there's a phase transition, can you do it to that accuracy? Yes or no? And potentially there can be other phase transitions as well that we haven't discovered. So this is potentially a very, very delicate issue and classification program that can come out of this. I mentioned briefly the solvability complexity index hierarchy, and a lot of the tools developed in that framework is very helpful to understand these types of lower bounds. All the upper bounds, then you have to construct the algorithm yourself, and that's also a very fascinating area and will require completely different tools. Right, I need to wrap up because I want to allow some questions as well. If you're interested in some, what should I say, more layman explanations of this, I recommend this article here in IEEE Spectrum, which try to highlight and also simplify some of these questions here for a general audience. So that might be worth looking at. So the stuff that I presented today is in this paper here. I also want to mention before I wrap up the connection to computer-assisted proofs. You may know that computational mathematics is now becoming a big issue in computer-assisted proofs in mathematics in general. There was a workshop at the American Institute of Mathematics last fall about this, and there's a report on that for which you might want to read about these issues. And computational mathematics in computer-assisted proofs is different than formal verification. This is really about using computations to enhance your toolbox in computer-assisted proofs. And optimization is a crucial part. And I want to mention, just before I wrap up, this famous problem, the Kepler conjecture, which is Hilbert's 18th problem, or at least parts of it, where you talk about the packing of snowballs or packing of spheres in 3 dimensions. And there's a famous program on this and a final solution to the problem. This is led by Tom Hales. Many of you would know the details here. And what is really interesting is that what is needed to solve or to prove Kepler conjecture is computations of 50,000 linear programs with, and here's the crux, approximations to irrational numbers. And it shouldn't be a great surprise that you will end up with, say, pi, given that this is a packing problem. And we getting directly into the issue of generalized hardness approximations. These are non-computable problems, but they only need to get this to one particular accuracy. And in the first paper that was published in this in Annals in 2005, then the accuracy they need is 10 to the minus 8. They improve this on the final solution to this in 2017, then the accuracy is 10 to the minus 6. And here's the point. You can compute with non-computable problems, even in computer-assisted proofs, but the generalized hardness of approximation might have a crucial impact here. But of course, you will never let epsilon tend to 0 when you're doing a computer-assisted proof. You will have to do this in finite time and say, here is the accuracy I need. And the point is that if you're on the right side of the phase transition, you're good. If you're on the wrong side, it might be a disaster. All right, I'm going to wrap up. And I want to mention some papers on this if you're interested. And then I'm going to actually end with some completely shameless self-promotion. Here's a book. And some of these issues are discussed in the book, but from a slightly more applied point of view. And I hope you like that. And with that, I thank you for your attention.
Thank you very much for the great talk. Are there questions from the audience? If so, just unmute yourself and post the question. I can start with one. How worried should we be about this?
That is a great question. I think you should be, well, you should be worried in the case that if you don't know, you should be worried. But in terms of research, I think you should be not worried, because what this means is that there's tons of interesting problems to look at and that the world is extremely complex. Well, the world is extremely complex that we knew. So it's a very good question. And that's why I also want to highlight this question, why should I care? So if you don't know anything and things are not working, it is very likely that this could be an issue. But as I pointed out, it is understanding the phase transition that's crucial. And if you're on the right side, you don't need to worry. And that's why I wanted to show also the issue with the computer-assisted proofs here, because as long as you can do this and you're on the right side and you have a verification of this, then fine. So I think what we also need to understand is that we can embrace non-computable problems. Non-computable problems have been essentially, scathed as bad things. Well, if it was the case that non-computable problems were not an issue in our daily routines, I would probably say, fine, we know that they're bad, let's avoid them. They're here, we're computing with them on a daily basis. That's the issue. So what we then need to understand is why are these non-computable problems sometimes a disaster, but sometimes actually completely fine. But it depends on the accuracy and it depends on the application. So to sum up an answer to your question, you may need to be really worried in certain cases, but there might be a saving way here. And mind you, when Tom Hales started this incredible program on the Kepler conjecture, of course, all of these things were completely open in the air. You simply have to go for it. And they were able to provide all the computational tools for this, despite this being non-computable, and able to essentially sail into the sunset. So there is a silver lining here that even though there might be difficult problems, you might actually be able to solve some great things regardless.
Okay, so we need to be aware that there is a limit, but as long as we're on the right side, things are kind of fine.
Things are kind of fine.
Yes.
I want to highlight this issue of randomness, though, because randomness here is really, really, really delicate. And I think that we also need to revise our understanding of how that works. And that I didn't emphasize too much on that. I could give a whole talk about that later on, but that's a different issue. I just would to give you a teaser. But I think understanding the power of randomness in a lot of these cases here is really delicate.
Yes. Are there any questions from the audience?
I have a question.
Please.
Thanks. So it seems like the difficulty comes up because you ask for the argmin, but if you're just asking for the minimizer, that's much easier, right? You don't have these extra problems. Is that correct?
Sorry, if you ask for just a minimizer, so the argument,
not a minimizer,
yeah.
Just the objective value. That's going to be okay.
Yes. Huge difference.
Okay.
Let me just talk a little bit about that. This is a great question. Let me talk about this. So when we go back to the standard linear programs here,
yes,
what has happened throughout the history, and this is really, really crucial. In a lot of linear programs that we use on a daily basis, it is the objective function which is crucial. And I'll give you an example. People can use this for, say, optimizing the time for, say, flight patterns, at Heathrow Airport. And what one tries to do there is to figure out, okay, there's a time constraint, and there might be a sort of optimal constellation of how you should get the planes coming into Heathrow Airport, for example.
Yeah.
And you're trying to run your optimization problem on that, and then you get, say, okay, I'm 10 seconds away from the true minimum in the objective function. And then an approximate minimizer of that could be very, very far away from the true minimum. The true minimizer. But who cares if that constellation of planes is very, very different from the optimal? Who cares? What I'm interested in, I'm 10 seconds away from the minimum. So who cares? And in many cases, this constraint here, the objective function will have a physical meaning. Time, energy, something that you would like to minimize. And that's what classical optimization has been about. And then this is not an issue because you really don't care about the minimizer. Well, it's a candidate, but if it's close to the argument or not, couldn't care less. Then there is a huge change in the demand from the community. And it happens late 90s, beginning of the 2000s, when all of these problems here now are used in other areas. We have, for example, using total variation in image reconstruction. statistical estimation, compressed sensing. These are huge fields. For now, suddenly it's the minimizer that's important. If you take compressed sensing, for example, what is the objective function there? It's the L1 norm of the wavelet coefficients of an image. Knowing that is so uninteresting that you wouldn't even look at it. It's the minimizer now that's going to be your image, if you will.
Yeah.
Numerous problems. All of these new mathematics of information, mathematics of data science completely changed the demand.
Yeah.
But now the question is completely different. I'm not interested in the objective as a lot of problems can be very interesting, but not in this case. Now I want the minimizer. And then the minimizer is a much, much harder problem than computing an approximation to the objective. And that's why I wanted to make this analogy with robust optimization, which is really about getting robustness when it comes to the objective function.
Okay.
Did that make sense, sir?
Okay. Yeah.
Yeah, I think there's time for one final question. If not, then let's thank the speaker again.
Great. Thanks a lot for your attention.
Thank you.
Yeah, I have one more question I did want to ask during the talk, but so the people can go off. But like, say, if instead of okay, is it possible that like, okay, so that you sort of beforehand recognize like that an instance of a problem is not going to be computable? Is it like I'm not sure this is a silly question, but like
No, this
can
is
you
actually,
say like
yeah, it's a very
like
good one.
give an LP like either you tell me like it's going to be the exit flag something, or like maybe you say it's not potentially not computable. I don't know.
I understand. This is a great question, and it's super subtle. I'm trying to understand that. I'll try to explain it. A statement about non-computability can only be about a class.
Class.
So if you take,
okay.
I'll try to explain this very carefully.
Okay. Yeah.
I'll try to explain this through sort of the standard things. You know, the halting problem, right? The question, the good old problem from Turing asking, can you write an overall algorithm that can check any other algorithm if it will halt or not on a particular input? That is a famous non-computable problem. Okay. But the issue is this: any problem is computable in the following way. There will exist an algorithm that can do that particular problem. The algorithm can say, yes, it does, or it doesn't, just for that particular instance.
Yeah.
The problem is that you need to have a class. So where you could find a particular algorithm to solve that particular problem. So what you're really asking is, will the algorithm that you chose for this class of computable problems be able to handle that particular problem? And this is where the exit flag comes in and say, no, you won't be able to even tell if you're wrong, if you see what I mean.
Okay.
This is the challenge there. So what you need is either to know where the phase transition is, or you need to know that you're in the safe area. The exit flag is not going to be helped to detect that. However, there's another subtlety. You could ask for a weaker exit flag. Exit flag that is failing on some input. Now, you don't want to have a false positive, meaning that it says that it's correct when the algorithm is wrong. Okay. So you can have a pessimistic exit flag that says, I don't know in certain cases. And it will say, I don't know when the algorithm is correct on certain cases. But it will, when it says it is correct, it will never fail. And this is essentially what you'll see in the formal verification of the Kepler conjecture. There's a formal verification there for which they can say, I don't know, but that when you get the certification, you're 100% sure. And then you get your 50,000 ones, even though these are non-computable, and you nail it, and then you have your great results.
Thanks. This helps.
Thank you.